if we have a data, after that we want to fit this data usually to get, for example, an equation for this data. Usually we use least square. Least square, it helps us to minimize the error. After that we can get an accurate solution to find a polynomial with order n that can fit a number of data, for example, n plus 1. So from this data we can give, for example, get an equation. Interpolation here, interpolation also study here. It's one method of the curve fitting, but here we usually focus how we can get the value at a certain get the value of the function at a certain value, and this value or this x not available in the table. For example, if we have a data, after that, if we have a data, for example, for Saturday, what's, for example, the number of people that's enter, for example, your restaurants, Saturday, Monday, until, for example, Wednesday, but you don't have any data, for example, for Friday. So what we want to have, we want, for example, to get a linear relation between this data and the number, for example, of the people that use this restaurant. So if you want, for example, to get expectation or estimation of the number of the people that it's expected, for example, to come at this day. Okay, if this day, for example, comes between these days, if we have, for example, number of table, after that we want to have to estimate the value of the function at a discrete point. And this usually, this point not available in the table that you have. We call this interpolation method. So interpolation method is one of the very famous method to find the value of the function at a discrete point. So usually it's used to estimate intermediate values between data points that we have. So if, for example, if we have n plus 1 data points, so there is at least one point of order n that can connect all these data, or base draw all these points. Should be base draw all the point, not like the least square. In the least square we have the point we minimize the error. If we have here points like this one, okay, we have certain point, we try to minimize the error or the distance between these points by select the best fit line. But here in interpolation, this line should connect all these data. Okay, should connect or base draw all the points that we have. Okay, so this is interpolation. And during this topic, we'll study two very famous methods. The first one will be Newton divided difference method. And after that, we'll study large or long range method, okay, which will be a special case of Newton divided difference method. Okay, so here usually we start with the sample version, and the sample version will study the linear relation. If we have a linear relation between the inputs and outputs, after that we put it in linear form. Okay, so after that we can expect any value of data. For example, if we have table like this one, I have x's and here I have the value of y's. So at x1 for 0, for example, I have y0, and this is 1, so this is 2, for example, and this is 3, for example, and this is, for example, 4, any values. So if I want to find the value 1x equal to what's equal, so this is interpolation method. It help us here to estimate the intermediate or the discrete points for example, between the tables. If we have any point, for example, here beside data points in the table, so it helps us to find or to estimate this value. And usually this method is very accurate if we use, for example, high order. If we increase the order, for example, from linear to quadratic or nonlinear, for example, version. So if we increase the order, so in this case the system or the estimation will be more accurate. Okay, let's take some examples later, inshallah. This will help us. Okay, so here, for example, in the sample version, if we talk about the linear interpolation, in this case, there will be only one straight line For example, first order polynomial that's connect the 2 points. Because here the first order, it's order 1 and equal 1. So it's connected 2 points. Okay, so the points that we need here, it's n plus 1. Okay, so here we have a straight line, only one line that space or goes through or connect the 2 data points. Here we don't have any approximation, that means we don't have any fitting that minimize the distance between the points. Here we have to connect the points. So polynomial interpolation consists of determine a unique nth order polynomial that's fit n plus 1 data points. So this polynomial or this method, it's provide a formula to compute the intermediate values. So we need to have a formula, for example, form of the polynomial of interpolation. After that, we can use this form to determine or to compute any values or intermediate values from the table by using the data in the table. So what's the fact that we can see here? This is the sample form of the interpolation here. It's connected 2 points. You can see here we have to connect 2 points, x0 and x1. Okay, so this is connected between the 2 points here. So if our goal, for example, to estimate the value of x. Okay, so this one, by using this data, so for example, x should be between the 2 points that we use. If I want to estimate x, I will take 2 points around it. If the interval increase, the accuracy will decrease. If we reduce the interval, we'll see this in the examples, so we will have more accurate solution. Okay, or we converse faster to the solution. Okay, so the error, the estimation error or the percentage relative error will be minimum if we minimize what we call this, the distance between the 2 points that we use. Okay, so for example, if we have here, this is here x and this is f of x. Okay, again, I think I will use this table. Let's increase this one, this here 6, for example, here, and this, for example, 8 assume any values. So if you want to estimate 2, one student may take, for example, 0 and 6. This will converse, but with a large error. But the best thing is we try to take the minimum interval. Okay, so 2 actually located between these 2 points, between 1 and 3. So it is better to take this interval only. And we start from this one. Another one might take, for example, 0 and 3, or 1 and 6. All these works because this is these intervals, for example, 0 to 6, also contain 2. Okay, the point 2. And also we have here 0 to 3 also contain the point 2 that we want to compute. But for example, if we reduce the interval, so in this case, our estimation will be accurate. Inshallah, we'll see this in the one of the examples that comes in these handouts. Okay, شباب until here. So interpolation here, it's just use it to estimate the value of the function at intermediate points by knowing, for example, a precise points around it. Okay, so just we connect the point here, for example, based on the, and this, because we have similar interval here, you can, or triangle here, this triangle and this triangle are similar. So in this case, it is easy to equalize the slope. And then, for example, we can compute the point, for example, or the function at x. So here, this is one of the examples that's we use it. We usually use it, this one. So for example, here, what's the sign, the question here, or find the sign of 0.15. And here you have a table of data. You can see, if you look for this table, I have 0, x equals 0, x equal 0.1, x equal 0.2, 0.3, 0.4. But what about x 0.15 or 0.15? I don't have in this table. So this intermediate interpolation method, it's one of the best methods that help us to estimate these values that's not available in this table. If we have accurate tables here, okay, or precise table. So here, for example, I will look for this one. Where is this located? It's located here. It's not located here. It's located here, for example. It's located at this point. Okay, so I will start from this interval. I will take these points to estimate the value of these the unknowns. Okay, so for example, by using a linear interpolation here, we find that by using this method, we find that the solution is equal 0.1493. While, for example, the true value with 4 decimal digits, it's equal 0.1494. Okay, you can see this value is usually accurate. This is a linear method. If we increase the order, usually will be more accurate. For example, if we use quadratic or nonlinear high order, so the system or the estimation will be more accurate. Okay. So what's this method, ya shabab? This method, it's usually we have here, because we have here similar triangles here. Okay, and from this connected line, or by computing the same slope here at this point, for example, if 1 of x, which will be the estimate of the point x that we want to estimate, because this we know that we want to estimate the function at this point. So we define it, for example, f1 of x. Okay, so this is f1 of x minus f0 of x over x minus, or the run here, x minus x0, or this slope. It's equal f1 of x will be the function at data point x1, will be this one, minus f1, or sorry, minus f0, okay, over x1 minus x0. Okay, so now this is unknown, we went to find. So by doing rearrangement here, okay, by doing rearrangement, we will have this first order polynomial. Okay, first order polynomial. So here, this is f of 0 is nothing. Usually this is given in the table. If I pick this one, I return back here. So if you look for this one, what we need. So this is the points that I need. I have here x0. What's x0? x0 is 0.1. I use it. Okay, and x1 is 0.2. So what's the function at x0? It's equal 0.0998. So I substitute here. Here, for example, I will put here 0.998, for example. Okay, so this will be plus. What I have here, I have, yes, yeah.
It is 0.0.
We use this interval. What's one?
Yes, it is 0.0998.
Yeah, 0 here. Yes, okay. Thank you. Okay, 0.0998. Thank you.
But doctor, it's supposed to be 0. It's 0.
Why 0? Because we use this x0 now. I don't use these points. This is x1 and this x0. I use these 2 points. Okay, this is the table. I take this point. If you take 0 and 0.2, you'll take 0 as x0. Okay, so we just select 2 points to find the linear relation. Okay, so after, yes,
sir.
Yes.
Isn't this just the average?
Yes, here what we do, we just here we take the slope, equalize the slope. If you look for this one, this is the slope here. This slope should equal this slope. After that, we compute it. Yes.
Okay. Thank you.
Equalize because this one line that's connected, we have the same triangle here. So in this case, both terms should be equalized, and we are interested to find or to figure out this one, f1 of x. So we just rearrange this one. All this is given. These points are given, and I want also to estimate the point at this one, for example, or point or 5, point 15, for example, in our example. Okay. And I have here, for example, 0.1 x0. X2 is 0.2. I know this point. All this point I just calculate to find the estimation of this function. And we call this divided difference. Okay, divided difference will be 1. So if we look for this one, we just have this x1. We know this one is equal, this point is 0.1987. And f of 0 is given 0.0998 over, for example, Lx1 is 0.2 minus x0 0.1, and multiply. This is the intermediate function, or the intermediate point that we want to find the function or estimate the function in it. This should be 0.15 minus, for example, 0.1. This should be 0.1. Okay, so these functions, I have it here. This is 0.1987. Okay, this point, I can type it here. You can check it using your calculator, Shabab, if you have. 7 should be minus 0.998. Okay, this should be over 0.2 minus 0.1. Okay, and this should multiply.
To find the true value?
No, true value, we use it directly using the calculator. This is the estimation.
Okay.
Okay, this is the estimation. We need the true value, use it directly using the calculator. So just take sine of 15. Using the calculator, check it. It should be 14.1494. This is using calculator. Okay, I think this should be degrees. Degrees here, this is the true value. The true value, you can compute it using the calculator. After that, you'll use the calculator to use this form to estimate the sine 0.50.
This is for radian, not degree.
Radian, the value?
Yes, I check it by calculator now.
You check it?
Yes.
You get the correct one.
In degree it is more small.
More small, okay.
In degree,
radian.
Yes.
Okay. Radians, okay. So this is 0.114, and after that we can compute the true error here, if you know. What about the estimation using double polynomial? You get the same value at this point for the estimation.
The estimation, it's like in the second one.
Yeah, this value, the same one?
Yes.
Correct, the calculation, okay. So after that, you can see the error, we have it power -1, -4, okay? So we have here a small error. Okay, so this method, we use it. Okay, Shabab, so here we'll use radian, yeah, Shabab, to do this table. Radians. Okay, so we have checked this one. So this is the formula, Shabab, that we use it. This is only for a first order system. So we call this usually, this is B0. To write it or to type it in linear equation, we call this B0 plus this slope, or this we call this divided difference, we call this B1. Okay, so we have here B0, B1 multiplied by the difference between the point that we are interested in to find the function, and this will be the start point. Okay, the start point that we have it here. So we call this linear interpolation method. So interpolation method, we can use it here to estimate the value of the function or the points that's not available usually in the table. Someone, for example, from you might use this point. Okay, or they increase the interval, use this point as x1, for example, and this point as x1, this x0 and x1, and try this one and see what will be the difference. If we have, for example, the error is minimized, the error is the same error, or the error is increased. And usually from the theory, the error should increase, because if we increase the interval, so in this case, the estimate will go far from the true value. Okay, so try this one and this one, or try this one and 0.3, or try 0 and 0.4, or try 0.1 and 0.4, like this one. Try to do, this is just a practice at home. For example, to practice when you use range exams, because you have table like this one, to have more examples, just change the data and try to compare between them. Okay, try to compare between them and check, for example, the true error. Just take one example and make from it, for example, 4 to 5, for example, practice problems. Okay, the same table, you can do a lot of problems from it. But the interval should include 0.15. You cannot take, for example, 0 and 0.1. Okay, so we need to estimate, or to estimate the point between the 2 points that we have. Okay, so this should be intermediate point. Any question here, Yashua? The methods, inshallah, easy, and it's need practice. And later, for example, we will have a form for this one. We will have a table for this one, and we'll see how we can use the regression method to find interpolation for polynomial of order n, for example. Later, inshallah, after we step by step, inshallah, we'll take examples. Any question up to here, Yashua? Okay, so after this, I'll give you another example. We have another example here. Okay, so as we said, we start from this one, and after that, we get this linear equation. So this is the linear equation, and usually we type it in this form, so as a linear form. So here B0 just represent the function at x0. B1, we call this the first divided difference. Okay, we call this divided difference, or we denote it by this form. Okay, so fx x1 x0. So no difference between in the value if you take x0 x1, the same value you'll get it at the end. Okay, the same estimate. So the order of data is not important here. Nothing will change. Okay, so you take it x0 x1 or x1 x0. So if we change the order of the data, this will not affect. Here, another example here, this from the textbook. The example here is 18.1 is to estimate the value of len 2 at the point 2. So if we have this data, for example, from the textbook, we have x's, we have point at x equal 1 equals 0. So len of 1 is equal 0. Len of 4, it's equal this value, and this is len of 6. So the question, find the len of 2. So by using your calculator, you can compute the true value, and the true value is equal 0.6931472. Okay, so this is the true value here, and after that we can do, for example, estimation. So for example, if I start with this one, I assume this is my x0 and this is equals x1. I take L1 point data, this is x0 and 6 as x1. So in this interval, I will include 2. So 2 is intermediate in this interval, but I take the maximum interval. I try to find, for example, to estimate the value of 2. I will take this one, this first. The second step, we want to compare this one when we take x0 equal 1 and x1 equal 4. That means I make the interval shorter. So also we want to estimate the value at this point. Let's see the comparison between these two methods. Okay, so when we have a larger interval from 1 to 6 and 2 is located here. Okay, or we take shorter interval and we'll see what's the difference if we, for example, here by using different intervals. But the mean point here, this point should be intermediate between x0 and x1. This is the very important point. So in this example here, for example, by using linear interpolation here, so here when we use, you can see this is f of 6, okay, minus here f of 0, or f of 1, sorry, f of 1. This is f of 1, or x0, we call this x0. I have here, this is the run here, I have x1 minus x0, so I have 6 minus 1. This is the point that I want to estimate the function at it here, minus x0 is 1. I will find the estimation of the function at x2, or x equal to. Okay, so I find it here, for example, 0.358351. If I take here the true relative or percentage true relative error, because I have the true value is 0.69314. So I take the relative error, it's equal 48.3%. This is for the large interval from 1 to 6. Okay, the interval here from 1 to 6. After that, if I take shorter interval, so here I evaluate the function again at point 2 by using the same things. I have here, this is f1, but here the function here at f x1 equal 4 minus if x1 or x0 equal 0. Here x1 is equal 4 minus x0 is equal 1. Okay, this is the value of x, and this is the value of x0. So in this case, I will get this estimation of the ln2. After that, because we know the true value, this is the true value that we have by using the calculator, we estimate or calculate the true value. So in this case, I can compute here the percentage relative error equal 33.3%. So in this case, we can conclude that by using shorter interval, we can reduce the percentage relative error to 33.3. So we can estimate, but if you use a larger interval, so the estimation will be not more accurate. So if we reduce the interval at the minimum interval that we have it in our data, for example, in this case, more estimation will be more accurate. So if we have huge data, we try to select the minimum interval that's contain this point we want to estimate. Okay, so one student, as we said in the previous example, we can start from 0, for example, to 6, and we went, for example, to estimate 0.15. But a good way is to reduce the interval as max as we can, as minimum as we can. So this graph represents the linear estimation of these functions. So here we have x0 or x equals 0. At this point, x equal, this is 1, and this should be 1. Okay, and this is 2, 3, 4, 5, and this is 6. Okay, and here we have another estimation. You can see this is the polynomial that we draw. This is the polynomial that we develop, linear polynomial or linear estimation, the line that we develop. So this equation represents the line that we develop. So if you wanted, for example, a general line, you will have here x. Okay, so we'll have here a linear equation that we develop. After that, this will be a general. If this is x here, and this is x, so I will have here a general equation or a linear equation in terms of x, order x. Okay, but if I want to estimate the value at a certain value, so I will substitute instead of x by 2 here, for example. So this, for example, the estimation, this is the true value. This should be the true value, and this point. And here, for example, this is the estimation when we use the interval from 1 to 6. Okay, and this is the line that's connected 2 points. So this is the estimate here for 2 at point 2 here. And this is the estimation when we use shorter interval. when we use here 4 and 1. You can see if we reduce the interval more, for example, we might, for example, we can reduce the error. If you can reduce, for example, the interval, if we take, for example, if we have 0.3, so the error also, I will get the point at this point now, or the estimation will be at this point. So if we reduce the interval, we can reduce the error or the estimation error. So this is the two-step of estimation. When we use the larger interval, I get the point here is a little bit far from the true value. When we use shorter interval, so in this case, we minimize the error of the estimation. Any question, يا شباب, for linear interpolation here?
Doctor, my question is there some application I need the error more than the smallest one, or always in all application I search for the minimum error?
We need application to, we look for the maximum error?
Yes, or error, we need error above something, above 2%.
Usually the error, for example, for our estimation, we have a tolerance in our estimation. If you want to do estimation, we need to have a tolerance. Okay, so otherwise, for example, if we have, if I accept, for example, in some application, we might accept it very small error. In some application, we need the error to be 0. Okay, and some application, it's not effect. For example, if it is, for example, 40%, 30%, it's not effect. But usually, as engineering, we try to minimize the error. Okay, so how we do design or implementation, we don't care about the error. So usually the main goal of our estimation is to minimize the error. If any function, any optimization. But for example, if you talk about optimization, you look for example, for profit. So in this case, we maximize. But when you talk about the cost and others, for example, one solution, the best solution that we can provide to our company, for example, or to for example, my calculation is to minimize the error. So this is the solution that we look for usually as engineer. Okay, so if we have, for example, any estimation, for example, any points here that you have, for example, about the cost, for example, of maintenance, for example, you have here, this is months, and this, for example, the cost. If you have, for example, the first month, what will be the cost, for example, 10,000, for example. Second month, I have 10,000 again. And for example, here, for example, or 10,000, let's see, 20,000. For example, the third month, I have 15,000 or 15.5 or larger than. Okay, let's say 12,000, for example. So here we need to, for example, if I went here, for example, you have the fifth here month, and we don't take any data, for example, for the fourth month. So what will be the error? So in our estimation, this is the estimation. Okay, so I do here the estimation of the cost, or the fuel that I use it, or the salary that I pay, for example, or these things. But this is the estimation. I want to compare this usually with the true, because if I don't have any comparison between the exact value, because if I have the exact value and the estimation, so in this case, sometimes the work will go wrong later. So usually we need to compare this one and to minimize what we call these the errors. In some application, for example, we do, for example, in control. If you look, for example, in control for control student, sometimes we do this in control, like for example, computing the error by using the feedback. We call these. We have here feedback loop, and this is the process. If you have this occur, and this is feedback. Here we usually use negative feedback. That means we try to compare the true value or the desired value that I want. This is the true or the desired value that I want. And this is the estimation for the actual value that we estimate after this loop. So we do here comparison. Some application we use positive feedback. That means we try to increase positive feedback. So in this case, we don't have reduction of the error. Okay, so usually this is a medical application. For injection, for example, they give you, for example, glucose, or for example, other medical application. But for example, as engineering application, I think usually we will go for minimizing the error. If you have any application, for example, any student, they read, for example, about any application, we maximize the error, just inform us to help us to just to note this.
Doctor, so it's better to use shorter interval?
Yes. Here, for example, if you want to estimate the value at, for example, month number 4, you have a lot of choice. You might select 1 and 5, okay, or you might select 2 and 5, or you might select 3 and 5. So all of them will give you estimation for this function, for at the function at x equal 4. Okay, because here this interval from 1 to 5 also include this point. From x equal to here, for example, and to x1 equal 5, also this include this point. And from this example, we can see when we use this table, here this is the table I use. I have here 2 choices. I need to estimate the value at 2, and 2 it's located between 1 and 4. But for example, one student may take 1 and 6. Take the larger interval. And if we compare this with the shorter interval, and this is our comparison here, you will see when we use shorter interval, we can reduce the relative error. But if you use larger interval, and this graph is just this the estimation, what we do is like here. So if we have, is take this point and this point. So the value of estimation is this point now. This is the estimation that we compute, this point that we compute. Okay, while the true value, this is the true value here. If you use larger interval, you can see when I use larger interval from 6 to 1, I will get this point. And you can see this is the error now, the distance between the true value and your estimation. If you use a shorter interval, so you will reach here. Okay, so you reach here. So in this case, this will be our estimation. And in this case, what we do, just you can see here the error is less than what we have before. So in this case, I think in general point, we can say that when we use shorter interval, usually it's reduce the relative error. Okay, that's what I know. What about the other graphs? I don't know if there is any pitfalls of these methods. I don't know, but I will look for this one. I'm not sure about the pitfalls of these methods. For example, if we have graphs in other shape, but this will be the usual point that we have. Any question here?
So again, Doctor, you said the shorter interval will be less relative error?
Yes, if you use shorter interval, this should provide less error or minimum error.
Okay.
And usually if we ask you, for example, to use here, for example, in the exam, for example, if you have like this point, use linear, and to estimate the point, for example, 2, usually you have to select this, or you should select this one. The minimum interval that's contained this one. Okay,
but in the example, he used the long interval. What's the reason here?
Here, just to show you a comparison when someone uses the shorter or the long interval.
Okay, good. Thank you.
Okay, so here just to do a comparison between the two methods. If someone, for example, use here the shorter interval from 1 to x0 here, for example, this is x0 and this is x1. This is one method. another one may take this one as x1, because this interval should contain the point x equal to. Okay, so in this case, if we take this point and this point, so we might find this comparison here. When we use the larger interval, we will have larger relative or percentage relative error. Okay, so I think also we'll search for this one if I have more examples about this one, or we look for bits fills of this method. I don't think so. This because this method usually it is improve the estimation. Okay, it's provide a good estimation with a good accuracy or the accepted accuracy. Okay, it's not that we don't have any fears of this method, as I know from my background. Okay, so the first things, as usual, we start with the linear method. So second method, we can go for quadratic. Okay, so if we need to improve the estimation more than what we have in the linear, so we can go with the highest order. So if we start, like for example, Tyrol method, as we increase the terms in Tyrol method, so we can increase the estimation. So if we take on, for example, x in Tyrol method, what we do if we take x, for example, xi plus 1, okay, just equal if, for example, of x0 or x1. So this will be the first term or zero order. As we take more terms, after that I will take the first derivative. Okay, x0 multiplied by h, and then, for example, second derivative, for example, and x0 multiplied by h square over factorial 2. Okay, so as we increase the terms, we can improve the estimation. So here is the same things here, because these methods usually is derived from Taylor. Okay, so here, for example, if we take more terms in this case, that will help us to improve the estimation here. So in this case, in the previous method, you can see I have here these points, I have here this the initial value, and here I have the slope. But here, to improve this estimation, we need to introduce some curvature pendant into the line points. So for example, if we take, for example, 3 data points, okay, instead of we have only 2, we can take, for example, 3 data points. So what will be the quadratic polynomial or parabola polynomial or second order form of the interpolation? So this is usually the form that we need. Okay, so this again the same function, f0, f of x0, and this is the first divided difference or the first law, and this the curvature. Okay, and here we need to estimate the value at this point. This is the x. We know the value of x0. We know the value at x0 here and x1. By doing rearrangement here, that means I multiply, for example, b1 inside this brackets. After that, we finalize with this form. But usually, no need, for example, to know the derivation here. We need to use the form that we need. So here, let's take this one. I want to show you this one because I need this equation here. I will pick it from. Let's cut this one. After that, I will post it here. Okay, so this if sub to x, it's donated to the second order interpolation polynomial. Okay, so here, for example, if you look for b0, b0 is not just f at x0. From the table, what's the point that you selected x0? After that, we compute the slope, b1. Okay, b1 is the first divided difference. So here I have x or f of x1 minus f of x0 over the interval order that I have it from x1 to x0. I have x1 minus x0. b2, we call this the second divided difference. Okay, here we increase the interval with 3 points. So here I have f of x2, comma x1, comma x0. So what we usually do, we take these sub-intervals. So I will say, for example, f of x2, comma x1, minus the second terms. I will take divided difference between x1 and x0. Okay, this x divided difference x2, x1, minus divided difference x1, this x1, and x0. Okay, this line not clear. Okay, so this over here we take the maximum run. You go from here from x2 to x0. So I will take here x2 to x0. The maximum run will take it here. Okay, so this divided difference f of x2, x1, we represented by this form. Okay, so here I have x, or the function at x2 minus the function at x1 over the run x2 minus x1 minus divided difference between x1 and x0. So here I will take f x1 minus f of x0 over x1 minus x0. Okay, all this will be over the run that we have, or the maximum interval that I take. For example, from here we have it x0 to x2. Okay, so this we have this the curvature. So that means here, if I know the value of x, so I can compute the value of b1 and b0 and b2, and then I will substitute here. And from the table we can estimate the value of the function, for example, at ln2, if you use the previous example. Okay, so this is the generalization here. This is the function, or the general function for an order n. If you want, for example, to take it order n equal 2, n equal 3, like this one. So this is the initial function, f of 0, plus the first law, x minus x0, plus b1, x minus x0, x minus x2, for example, like this. Will go like this one until ends. And this will be, we call this the first divided difference. We have here f of xi, xj. So this equal function at xi, so the point that we selected equal xi minus xj over xi minus xj. We call this divided difference because here we do divided and we compute the difference. This second finite divided difference, so in this case we take 3 points, so 2 by 2. So we take 2 by 2. So we have here function, or divide the first divided difference of xi xj minus the first divided difference xj xk. And here at denominator we take the maximum interval, so this will be xi minus xk. Okay, so this will be for order n. You can see here I take, for example, n in order n, so usually here at denominator will be the maximum interval. Look, return back to the example that we take before about the len of, if you want to estimate the len, or len for x equal to. Okay, but here we'll take 3 points. The 3 points we'll use it for the estimation. So this is the quadratic form for interpolation polynomial. We want to compute these coefficients from the table that we have. So here, as we know, here what I have x0 equal 1, x1 equal 4, x2 equal 6. So if at x0 equals 0, if at x1 this point or this number, and here I have the function at x2. So here use the polynomial to evaluate len2. Okay, to evaluate len at 2, and 2 is not available in this table as we used before. Before we estimated using the linear estimation, and we find two types of errors, 48.3 and 33.3%. So if you want to do this one now by using, we increase the order of the polynomial. After that, we can estimate the error. So b0 is nothing, just the function at x0. So the function at x0, b0 equal the function at x0, and this equals 0. b1 just the slope or the first divided difference. So what we have here, so this is equal f of 1 minus f of 0 over x1 minus x0. Okay, so this is b1, it's equal f of 1 minus f of 0 over x1 minus x0. So if we take the values from the table here, we just substitute and we find b1. After that, we need to compute b2. b2 is the second divided difference, so we take 3 points. So f of x2, x1, x0. So in this case, I will take the first divided difference between the first 2 points minus first divided difference between the second 2 points over the interval x2 minus x0. So here I will take f of x2 minus f of x1 over x2 minus x1, minus here f of x1 minus f at x0 over x1 minus x0 over the maximum run that we have, x2 minus x0. So by the direct substitute here, we find b2 equal this number. So now we have the value of b1 and b2, and we need just to substitute inside this polynomial. And I know the value of x1 and x0 and x. So here we just substitute in the polynomial. If we substitute in the polynomial, we find the estimation of len2, it's equal this value. Now, if we compute the percentage relative error or the true percentage relative error, it's equal 18.4. Okay, so you can see it is a reduced quadratic from 33, 33.3 33.3, for example, to here to 18.4%. Any question here?
Yes, Doctor, the numbers are given. I mean, x0 equals to 1 and f of x of 0 equals to 0. These will be given in the example, right?
No, I will give you the table like this one.
Yeah, but what should be given?
Yes, yeah, should be given. Yeah, you need the data. You need the table. I will give you a table. This is x and this is f of x. Okay, so you will select this x0, this will select it x1, and this will be x2. You will select them in order in the table. Okay, so you have here this x1, this x0, this x1, this x2, like this one. After that, you just use the form. You need to compute this coefficient, the first divided difference and the second divided difference. And then you will substitute here, you will compute the solution or to find the solution. Any question, ya shabab, here? Until here.
Yes, Doctor, the true error is given.
The true value or the true error, the true value.
That is true value.
Yes, true value sometimes we give you And sometimes you can use, I will inform you, you might compute the true value using your calculator. Okay, so for example, then you can use the calculator to find the true value. So the true value we computed using the calculator that you have. More questions, Shabab? Okay, so let's go to the steps that we have here. This is the steps. The first step you will select, as our brother asked about, I will select the points that I have. So x0, x1, x2, like this one. So also we initiated with the functions. What's the value of these functions or the function at this point? If at x0, if at x1, and if at x2. After that, I will use the form of the finite divided difference to compute b0 or b1 and b2. And then I will use these functions or these parameters to substitute in the function. By doing this calculation, multiplication here, I will get this calculation. So after that, I will compute. This is the estimation of the function of x if when x equal to. Okay, so this is our estimation with error equal 18.4%. Okay. So this is general form, as we said. This is general form of the interpolation. As we said, this interpolation it's used to estimate the value or intermediate value between the point that we have. Okay, and this polynomial. So we usually create a polynomial, and this polynomial of order n should connect all the points that we have n plus 1 points, or it's best through all these points. So this is the regression here. After that, we can represent this divided difference in terms of regression, and usually this is what we give you during the exam in this form. So we give you here alterations, the number of alterations, and this is the x's, the value of x's, and this is the estimation. Here we need to compute the first divided difference and the second divided difference and the third divided difference, like this one, dependent on the data that you have. So after that, what will be the polynomial? We usually take this row, the first row, like this one. So this represents b0, b1, b2, b3, like this one. Okay, so this is the first row that we use. Here this will be b0, b1, this will be b2, b3. We'll take this one and we'll put it in the polynomial that we have. So in the coming examples, I will have here one example or small example that would help us to understand how we can fill this table. So this is the table that we have to estimate this data. Okay, for a second divided difference, second order divided difference. That means we use 3 points here to estimate the quadratic form. This is usually the data that's given. This is the x's and this is the y's, and the student need to fill these points. Okay, in the coming slides we'll see how we can compute these coefficients and these coefficients. Okay, and what will be the polynomial that we have. So the first 2 columns in the red one, this one is not only just the data that you have in the table. Okay, this is the table that you have, and we'll put it in this form. So this is the x's and this is the y's, or f of x. The third column here represent the first order difference or the finite divided difference. The fourth one, the second order difference. Okay, the fourth one or the fifth will be the third order, like this one. So how we compute this one? So the first order divided difference, as we know, this coefficient, we find it by in this form. So I have here f of x1 minus f of x0 over x1 minus x0. This is the first order divided difference. So if at x0 or x1 equal minus 3, here is the value minus 3, minus f at x0 equal minus 5, so I have minus 3 minus 5, over x1, not only just 1, and x0 is 0. So I will take the first order divided difference, minus 3 plus 5 over 1, so I have here positive 2 over 1 will be 2. So this will be the first divided difference. I will do the same for the second one. So I complete column by column. For the second column, because I need these two to find this one. Okay, I cannot directly compute this one. For the second column here, I have here divided difference between x2 and x1. So here I will have f at x2 minus f at x1 over x2 minus x1. So this will be minus 15 minus 3. So this is the function at x1 and this is the function at x2. Over x2 is minus 1, minus x1 is 1. So here I will get the value 6. Okay, so this is the first divided difference. If you have more points, you will complete this point. If you have the fourth point here, okay, so you will do first divided difference here. Okay, because we don't have, so no need for this one. So the next step, we want to compute the second divided difference. So for the second divided difference, you can see the second divided difference, I have x at k plus 2, x at k plus 1, x at k. So the interval here will be x plus k2 to x plus k. Okay, so if we have this point at x2, so the starting point will be at x0. Okay, so what we need here, and also what will be in the numerator here, I have the first divided difference, these two. I will take difference between these two. So this will be divided difference between x2 and x1 equals 6 minus the divided difference between x1 and x0, this is equal to, so I have it here too, over the maximum interval now. The interval, I will not take these two, I will not take 1 and 0, I will take x2 and x0. Okay, so in the first one, when we talk about the first divided difference, I will take x1, x0, x2, x1 like this one. So when we'll go to the second, I will jump 1 because here I have x2 and x0. Okay, so here this point, I will take this one and this one. If I have another row here, I will take this point, for example, x3 with the x1. Okay, so we jump 1. So the column after will jump 2. Okay, so like this one. Okay, Shabab. So here I will use this one. So I will use the first divided difference here. No need to compute it again. I will use it here. So I will take the difference between x6 here minus 2 over the interval that I have it here minus 1 and 0. Okay, because here I have this interval between 2 and 0. If you increase this one, if you have, for example, the point at this here, if you want to compute and I have row here. So if I have here x3, okay, so this should be 1. Okay, so take x1, 3 and x1. Clear this one, Ishba?
Clear, Doctor.
Yes.
Okay. Okay, so if we compute this one now, if we fill the table until here, so as we said, we need the first row to fill the equation or to find the equation. So this is the polynomial that we have. The quadratic function is equal f at x0 plus the first divided difference or B0. Okay, it is B1, sorry. ال B1 يا شباب this coefficient. Okay, ال B1 we have this coefficient. This B1, this B0. I cannot type here, but this B0, and this will be B2. The first row. Okay, so here we take this one. F of 0 is this coefficient, or B0, this coefficient. B1 just 2, I multiply 2, so this is B0 multiplied by x minus x0, plus this should be B2. This is the second divided difference, this will be here, minus 4. I multiply this by x minus x0, x minus x1. Okay, so I just substitute. After that, for example, if you want to substitute or to find the function, any value of the function, for example, x equal any values here between these 2 points or between these 2 points, I just substitute to find the value of x. Any question here until here? Okay, so this is the other example from the textbook that we have. Here, for example, if you want to find, for example, the third order Newton divided difference. Okay, so here the third order Newton divided difference. Before we have these 3 points, so if we have, now we need 4 points. Okay, 4th point at x3, for example. x3 equal 5, so the evaluation of the function is equal this point. So if you want to find the third order polynomial, so this is the third order, is equal B0 plus B1 multiplied by x minus x0 plus B2 multiplied by x minus x0, x minus x1, B3, x minus x0, x minus x1, x minus x2. So what we want to do here, we have the data that we have, this is the table. After that, we might do it using the regression, or you can compute it like this one. So if you arrange your data, you can put it in table here. Okay, the value here, you put it in table. After that, you compute the first divided difference. Inshallah, I will revise this one. I will put here a table and to put this data in table. Inshallah, for the slides to be clear for you, inshallah, how you can compute the first divided difference. And after that, the second and the third. So if we have data here, so the first divided difference, we take this point. I have the function at x0 and x1. So what's the value? This is the value if x1, so this point, minus f at x0 is equal 0 over x1 minus x0, and this will be the first one. Okay, and we'll call this B1 here. And then I will compute the second column, or the second column, a third row. This will be this coefficient, or the second row. So here I have x2, the first divided difference between x2 and x1. So this is the value that we have from the previous example, and we take the run between 6 and 4. We find the value, and also we compute the first divided difference between x3 and x2. So this is the first column. Here, for example, if you return back to this column, to this table, just we compute these 3 coefficients now. Okay, if we have 4 data, so I have these 3 coefficients. So second term, I need to compute the second divided difference. I will get 2 from 3, because these 3 terms here, I will get 2 terms. Here, so this will be the second divided difference. I will take 3 points now, x2, x1, and x0. So I will get benefit from what I compute here. That what we compute, this one and this one. I will take this minus this one, and over the interval 6 to 1. Okay, so here I have this point minus this one, and 6 to 1. And then I will take this point minus this point over the interval here 5 to 4. Okay, because here we jump 1. We jump 1 point. So after that, I will compute the second divided difference. And then the third divided difference, I will take these 2 points that I compute here, the second divided difference. But now the interval, I will jump 2 points. Okay, here we have the columns. You can see I have 1, 4, 6, 5. And third divided difference, I will take this one, this interval from 5 to 1, because the points here I have from x1 to x0. So this is the run here will be 5 minus 1. And this is already computed in the second divided difference. I have here, I will take these 3 points, x3, x2, x1, x3, x2, x1, these points equal this number, minus this point x2, x1, x0, x2, x1, 0 is given here. So to compute the third divided difference. So after we compute in this one, I just substitute. Okay, I just substitute and the table will be easier for you. Okay, so these coefficients that contain x0 usually will be b's that we have. Okay, that's contain f0 here. And this is the function at x of 0. So that's contain this one will be b0 equal f at x0. The first divided difference that contain x0, this is b1. And this will be b2. And this will be b3. Okay, so here just we substitute. I have b1, this coefficient. I will substitute it here. b2 is this value. And b3 is this value. I substitute, and after that we can estimate. So now when we use the third order polynomial, our estimation is equal 0.62. So if we represent this, or if we compute the true percentage error, so we can see it is equal 9.3%. Okay, so it is reduced by half. Okay, so until here it is, I will stop, and next class inshallah I will repeat this example again.